Hey guys, welcome to what is now take 3 of chapter 16, part 2. And we're picking up and we're talking about something called the acid ionization constant. Which is abbreviated as capital K sub A. And you may be thinking, wait a second, wasn't capital K what we used for equilibrium constant? And if you're thinking that, you are correct. And it is correct here too, because the acid ionization constant is just the equilibrium constant of a weak acid. If we draw out the equation, the equilibrium equation for a weak acid dissociating into protons, hydrogen ions, and a conjugate base, we're going to call it A minus. Okay, the equilibrium constant expression for this reaction, and I'm also going to say that each of these are in the aqueous state. All right. The equilibrium constant for this expression is just the concentration of the products over the concentration of the reactants. All right. And since this is an acid, we just put a little subscript A there, and we say that it's the equilibrium constant of an acid, or the acid ionization constant. I will not use this term acid ionization constant a lot. We mostly in chemistry, you talk about the Ka. So just know that the Ka is the equilibrium constant of an acid. And as we know, the larger the Ka is, the more product is made. And in other words, for a weak acid, that means the more dissociation, the more product there is, that means the more dissociation of the acid there is. And so the larger the Ka value, the stronger the acid actually is. So weak acids only partially dissociate, but if you refer to a table of weak acids, either in the one provided for you by me, or one in your textbook, or one you find on Google, you'll see a list of weak acids, and then next to it you'll see their Ka value. And usually they're ranked with the highest Ka value on top. So these are the stronger of the weak acids versus the weakest of the weak acids. All right, so even though they are weak, there are relative differences in their strengths. Alrighty, so we are going to continue on this idea of an equilibrium constant of acids and bases. We're going to sort of take a tangent and talk about the equilibrium constant of water, because in pure water, something interesting happens. It's called the autoionization of water. All right, it literally means self-ionization. So water can ionize itself. If we have two water molecules here, H2O and H2O, and they get close to each other, sometimes, because they are polar, that those hydrogens are very partially positively charged, and the oxygens are very partially negatively charged, that one of these oxygens will actually pull on the other hydrogen and end up snagging a hydrogen from its neighbor water molecule. So you end up with H3O plus and OH minus, two ions. Remember, ions are just anything that have a charge, a positive or negative charge. So basically, water just ionized itself. Another shorthand way to write that is just take a water molecule and show its reversible dissociation into hydrogen ions and hydroxide ions. So we can write out an equilibrium constant expression for each of these equations, where it's product, aqueous product, H3O plus times OH minus, over aqueous reactant. But notice that the reactants, the water molecules, are all liquids, so they don't actually go into the equilibrium constant expression. And for this bottom version, we would write it like this. Remember, in acid-base chemistry, hydrogen ions and hydronium ions are basically the same thing. They're equivalent. So since this is the equilibrium constant of water, we put a little W down there. We call it the KW, or it has its own special name. It's called the ion product of water, but most people just call it Kw, and we all know that K equals the equilibrium constant. At 25 degrees Celsius, Kw equals 1 times 10 to the negative 14th. All right, that is a constant. You should probably memorize it. I mean, you basically will memorize it by the end of doing problems in this chapter, but you don't have to. It is a constant that people look up and that will be on a reference sheet for you for the test. Okay, so since water is neutral, we know that water is neutral, and the definition of neutral is that it means that it has equal numbers of hydronium and hydroxide ions. So we can say that the concentration of hydronium equals the concentration of hydroxide in water. And we know that since the Kw of water is the concentration of hydronium times the concentration of hydroxide ions, all right, at 25 degrees, we know that this value is 1.0 times 10 to the negative 14th. And if we know that both of these values are equal, we can plug in an x for each one if we want to figure out what the concentration of each of these is in pure water at 25 degrees. We say that we have x amount of each, and x times x, another way of saying that is just x squared. And so we can solve for x, the concentration of hydronium and hydroxide in pure water, by taking the square root of each side. The square root of this is 1 times 10 to the negative 7. So x is 1 times 10 to the negative 7. In other words, in pure water, the concentration of H3O plus hydronium is 1.0 times 10 to the negative 7 molar, and the concentration of hydroxide is also 1.0 times 10 to the negative 7 molar. All right, so in pure water, which we know is neutral, a neutral solution is defined as having an equal amount of hydronium and hydroxide. It's not that it has 0 hydronium and hydroxide, which a lot of people think that neutral means there's no acid or base molecules. All right, hydronium, a lot of hydronium makes something acidic, and a lot of hydroxide makes something basic, okay? So acidic solutions are ones that have greater amounts of hydronium than hydroxide, and basic solutions are ones that have more hydroxide than hydronium. You may have questions in the homework that just basically give you values of hydronium and hydroxide and then ask you, is it acidic or basic? So the important thing to remember is that all solutions have both hydronium and hydroxide, and that always the product of the concentration of hydronium and the concentration of hydroxide will equal 1 times 10 to the negative 14th, as long as we're at 25 degrees Celsius. Okay, so we can calculate, for example, if we have the concentration of one of these ions, we can calculate the concentration of the other. So in this problem, it says calculate the concentration of hydroxide at 25 degrees for each solution and determine if it is acidic, basic, or neutral. So this first problem, all right, it says we have a concentration of hydronium that's 7.5 times 10 to the negative fifth. So what is the concentration of hydroxide? Well, we know that Kw equals the concentration of hydronium times the concentration of hydroxide, and that at 25 degrees, this equals 1 times 10 to the negative 14th. So we just set up that equation here. Kw is 1 times 10 to the negative 14th, and we're given the concentration of hydronium, 7.5 times 10 to the negative 5th, and the concentration of hydroxide is our X. It's what we're trying to solve for. We divide both sides by 7.5 times 10 to the negative fifth. And we get X, which is our concentration of hydroxide, is equal to 1.3 times 10 to the negative 10. It's a concentration, so we need units, molarity, molar. All right, for this one, same setup. You may want to pause the video and try it yourself and then check your answer. All right, equals 1.5 times 10 to the negative 9 times X. So divide both sides by 1.5 times 10 to the negative 9 to solve for X. I'm not going to walk through the algebra, but if you have questions, just text me. All right, equals 6.7 times 10 to the negative sixth molar. All right, so make sure you also practice typing this into your calculator, doing division and multiplication with numbers in scientific notation. It's important to make sure that you can do it, check that you can actually do this in your calculator and get the correct answer. All right, so these numbers, speaking of numbers in scientific notation, they're kind of a pain to work with, a pain to type into your calculator. Having to use that EE function is how I do it. So I would type in, for this number, I'd type in 1.5 EE negative 9 is how I type that into my calculator. And that's kind of a pain. And working with things in terms of these scientific notation is kind of a pain. Oh, I forgot in this problem. It also asked us to identify whether these solutions are acidic, basic, or neutral. So in A, we had 7.5 times 10 to the negative fifth molar of hydronium ions and 1.3 times 10 to the negative 10th molar of hydroxide. So there's a greater concentration of hydronium than hydroxide. So this one is acidic. And in the second one, if we look at these two concentrations, the concentration of the hydroxide in this case is greater than the hydronium, and hydroxide is indicative of a base. So this we would say is basic. Okay, so looking at these, comparing these numbers in scientific notation can be just a little bit clunky. And so someone, I don't know who, I should probably look it up, decided that it would be easier if we took the negative log of these and just had a scale from using like single digit numbers. That's easier to process and easier to look at. And we call this the pH scale. And it's called the pH scale for a very good reason. The pH is simply the negative log of the concentration of hydrogen ions, or it's the negative log of the concentration of hydronium ions. You can write it either way. Remember, hydrogen and hydronium are essentially the same thing in acid-base chemistry. Right? P just means the negative log of something. So pH stands for the negative log of H, the hydrogen concentration. So that's why it's called the pH scale. The inverse of, so we can use the concentration of hydrogen or hydronium to figure out the pH of a solution. If we want to go the opposite, if we have the pH and we want to know the hydrogen ion concentration, the inverse of these equations is 10 to the negative pH equals the concentration of hydrogen, or in terms of hydronium, same thing. Okay, so let's put these equations to use on the next page. If we have a solution and the hydronium ion concentration is 1 times 10 to the negative 3, the negative log of 1 times 10 to the negative 3 is 3. If we have 1 times 10 to the negative 4, I should have concentration units here. All right, then the negative log of that is 4.00. The negative log, I guess you can see a trend here, of 1 times 10 to the negative fifth is going to be 5.00. All right, notice the trend is that when you take the negative log of something in scientific notation, that exponent on the 10 is indicative of what the answer of the pH is going to be. So we can estimate that the pH for this next one is going to be about 9. And if we do the math and we do the negative log of 2.5 times 10 to the negative 9, we get a pH of 8.6. And that is indeed close to a pH of 9, which we estimated. Using this estimation is really helpful for making sure that you get the right answer, especially because typing in the negative log of a number may or may not be so easy on your calculator. If you're using a graphing calculator, you just type it in as written. But if you're using like an iPhone calculator, I had to type in 2.5 EE negative 9, and then I hit log, and then I hit negative, is how I do it. So it's a little bit backwards. All right, this fifth one here, we're going to estimate the pH is going to be about 11. And when we type it in, the negative log of 6.9 times 10 to the negative 11th, we indeed get a pH of 10.16. So it's actually closer to 10 than 11. And this makes sense because if we look at this diagram down here, right, the concentration of hydrogen ions is on the bottom and the pH value is on the top. All right, so for each pH value that we move, we're actually decreasing the concentration of hydrogen ions tenfold. But if we look up 6.9, a concentration of 6.9 times 10 to the negative 11th, that would be somewhere between 10 to the negative 10th and 10 to the negative 11th. That'd be right about here, which means that we should have a pH of about 10.16, and that is indeed what we got when we calculated it. So using that estimation technique is really good to sort of mentally check your answers to make sure that your calculator is giving you the right answer. So I encourage you to do that. And sometimes in a problem, you may just be asked, is this acidic or basic? And you might not even need to calculate the pH if you just use the estimation technique. So how do you know whether it's acidic or basic? Well, acids are this side of neutral. pH of less than 7 is indicative of an acid. A pH of 7 is neutral, and a pH that's greater than 7 is basic. And I saw a meme online that I thought was really clever and funny, and it said, "You're a 10, maybe on the pH scale, because you basic." And then I do a snap. Okay, so that helps you remember that high pH is basic and a low pH is acidic. And that is kind of backwards to people sometimes. So remember that low pH is more acidic, and a high pH is less acidic. It's more basic. So this wording can be confusing to students sometimes. As the pH increases, what happens to the acidity? The acidity goes down. All right, it becomes less acidic as the pH gets higher. So understanding that relationship of pH to acidity and basicity. So now for some more calculations. These problems give us the concentration notice it gives us the concentration of the hydronium ion or the hydroxide ion, and it asks us to calculate the pH of each solution and indicate whether it's acidic, basic, or neutral. So for the first one, for A, it's easy. It gives us the concentration of hydronium ion, so to calculate the pH, we just take the negative log of that. The negative log of 1.8 times 10 to the negative 4 is 3.74. And probably before I calculate that, I should just do an estimation. I'm estimating that the pH is about 4. And I got 3.74, so that checks out. okay? And a pH that's less than 7 is acidic. All right, in this second problem, it gives us the concentration of OH, of hydroxide ions. So first we need to calculate the concentration of the hydronium ions and then take the negative log of that. So we use that Kw equation. So remember, Kw is always equal at 25 degrees. And we're assuming these are at 25 degrees. If it doesn't say otherwise, times 10 to the negative 14th equals the concentration of hydronium, which we're trying to solve for, times the concentration of the hydroxide, which it gives us. I'm going to move this to the other side of the equation and divide both sides, just rearranging it algebraically. And so I'm going to divide this by the concentration of the hydroxide ions, so it's 1.3 times 10 to the negative 2. So I get a hydronium ion concentration of, drum roll, 7.7 times 10 to the negative 13. So if I'm estimating the pH here, I expect it to be about 13-ish. So now I just need to get the pH, I take the negative log of that concentration, 7.7 times 10 to the negative 13. And it's a concentration, it should have units of molar. Terrible about that. All right, so I get the actual pH is 12.11. All right, which is between 12 and 13. So cool, my estimation checks out. Now you try these two. Pause the video, try them yourselves. And I'm just going to write out the answer for you to check. And if you can't get that answer, text me, let me know, and we'll figure it out. So for this one, I'm going to estimate the pH should be about 9, and when I calculate it, I get a pH of 8.02. All right, which is actually, it should be closer to 8 because 9.5 times 10 to the negative 9 is almost 10 to the negative 8. And then for this one, part D, I have to calculate the concentration of H3O plus first. And I calculate that to be 1.4 times 10 to the negative 12. And so I am expecting the pH to be about 12. And when I take the negative log of that, I get a pH of 11.85, which is pretty darn close to 12. All right, so hopefully you did that work out yourself and you got these answers. And if you didn't, let me know. So a sort of shortcut that we can use, something else we can do, is talk about the Poh scale. If the pH scale is just, if pH is the negative log of the concentration of H, then hopefully you guessed correctly that the POH is just the negative log of the concentration of OH, of hydroxide ions. And the inverse of this equation is that 10 to the negative POH equals the concentration of OH, hydroxide. All right? And since the concentration of hydroxide times the concentration of hydrogen ions equals 1 times 10 to the negative 14, the pH plus the POH equals 14. Basically, the negative log of this and the negative log of this. It's basic. I can't derive it for you right now, but it has to do with taking the negative log of everything. And so the pH plus the POH equals 14. So we can use this equation as a nice shortcut sometimes to figure out some math involving pH. So this practice problem here says calculate pH and POH of each solution. So in these problems, you always want to pay attention to which ion concentration you're given. Notice that this one is different. It's the OH concentration. So for this one, we're going to calculate the pH first. So we just take the negative log of this hydronium ion concentration, 1.7 times 10 to the negative 8th. And we get a pH of 7.77. And now to get the pOH, we can just do 14 minus 7.77. Instead of having to figure out the concentration of the hydronium ion, we just do a little subtraction. Much easier. So it has a pOH of 6.23. I would say that this solution is slightly basic. It doesn't ask to identify, but I would say it's slightly basic. It's greater than 7. It's almost 8, so it's on the basic side. Second problem, very similar. It's giving us the concentration of hydronium ions. Maybe you want to pause here and try to answer the rest yourself before checking your answers. Just going to take the negative log of 2.2 times 10 to the negative 6, and we get a pH of 5.66. That's acidic. And the pOH we can calculate using subtraction. 14 minus 5.66 equals 8.34. And that's the pOH. Now for this last one, we're given the concentration of OH. So I'm going to start by calculating the pOH. Negative log of the hydroxide ion concentration is a pOH of 10.34. And then to calculate the pH, I just do 14 minus 10.34, and I get 3.66. Now remember, the pH scale is what determines if something is acidic or basic. So it's the pH here that determines that this would be an acidic solution. So pOH can be a helpful sort of shortcut to determine the pH from the, if you're given the hydroxide ion concentration. So this little trick could have made some of those previous problems actually a little bit easier. So that's where we're going to stop for this lecture. We're on about halfway through page 7.